My name is Christopher Jones. I will be presenting tunable nanoparticle surfaces for advanced propulsion under the direction and guidance of my mentor, Dr. Brandon Kemp. In 2015, an article published in Nature Photonics demonstrated that a graphene sponge could be propelled when the material is excited by a diode laser. This enhanced optical propulsion was theorized to be due to the negative momentum of ejected electrons, which can be seen in Figure 1. Using Mie scattering and force calculations, the momentum reversal was determined to be due to a nanoparticle's size and shape. It is important to note that Mie theory offers an exact solution for spherical scattering and has been used to validate approximate methods throughout the duration of this research. Further research utilizing Mie theory revealed that negative index materials were not required and the effects in rods could be tunable through light polarization. Figure 2 to the right has been used in my research to verify various methods of lossy analysis for Rayleigh theory. The objective of this research is to create a model for momentum reversal in nanoparticles, demonstrate tunable properties with light polarization, develop a surface based on an array of particles, and use multiple scattering theory for Rayleigh particles. The establishment of a proper algorithm for relating the results of Rayleigh theory with that of Mie is difficult due to the separation of total force into free and bound carrier forces. This is one of the main objectives of this work and has been the source of most complexity. The fields are derived according to the scattering potential analysis of the particle, which will directly result in the vector matrix representation seen in equation 1. This form is of the utmost importance because it allows for the analysis of both single and multiple particles from any incident direction. The polarizability describes a particle's ability to become polarized and is given in units of volume. The complex form used for this research has been proven to satisfy the conservation of momentum. This is accomplished by the inclusion of a dynamic term describing the radiation reaction seen in equation 4. These equations encompass the standard method for deriving the forces. It has been shown that the total force can be split into the gradient and scattering force seen in equation 7. The gradient force refers to the force due to the gradient of the field intensity, while the scattering force refers to the force due to the momentum of the electromagnetic wave. It should be noted that the scattering force seen in equation 9 provides a simplified means of obtaining a valid approximation of the force. The total force is given through the integration of a surface that just encloses the entire particle seen in Figure 3a. The problem of bound and carrier force separation for this analysis is due to the nature of applying the Rayleigh fields with equation 11. Two aspects were considered, which include a method for obtaining the internal fields and the bounds of integration for the free carrier force. To obtain the internal fields needed for integration with equation 11, we apply the boundary conditions and phase matching. Utilizing the tangential constitutive relations, which augment the electric field in the normal direction as a ratio of bound over particle permittivity, we arrive at the internal field. The bounds of integration for the force on free currents using equation 11 are set just inside the boundary of the particle as seen in Figure 3b. The force on bound currents and charge is then found using equation 12. For multiple particle analysis, individual Rayleigh particles are treated as dipoles. From the expanded form of the partial scattering field equation, it can be shown that this term results in a summation seen in equation 13. Figure 4 demonstrates two core shell nanoparticles due to Rayleigh scattering. Figure 5 was used as a means of validating the total force with the results of Mie theory. The major conclusion is that the integration of the Minkowski stress tensor is validated and that the scattering force equation provides an adequate approximation for rapid calculation. Figures 6 and 7 represent the results from the lossless case for wavelengths of 1064, which is a 20th of a wavelength and therefore well within the Rayleigh regime seen on the left, and 532 nanometer, which is a 10th of a wavelength seen on the right. These results were vital as an initial step to establishing a path to multiple particle analysis. Figure 8 describes the range of wavelengths in which Rayleigh analysis is relatively accurate. It can be seen in this figure that the accuracy of Rayleigh theory diminishes as lambda goes to 0. Therefore, it can be concluded that our method delivers the expected results for accuracy within the Rayleigh regime. Lossy analysis is vital for demonstrating material interactions within predetermined environments. Figure 9 to the left displays a low-loss system. The force on bound carriers goes from negative to positive, which is backed by prior findings. Figure 10 on the right demonstrates a higher loss system, which for a positive permittivity value is relatively accurate. Since Mie theory is highly complex for computational purposes, it is more advantageous to apply Rayleigh theory for the analysis of multiple particles. For these studies, the time harmonic fields utilizing the Minkowski stress tensor were used. Consideration for the bounds of integration for the time average force was then given in the determination of the total, free carrier, and bound carrier forces. In the future, the method of integration for the Minkowski stress tensor will be applied to multiple particles. Once the code has been validated, materials and surfaces can then be studied and applied in accordance. I would like to acknowledge the following. The following are references used for this presentation.